How's everything going? I will be speaking in English, I'm sorry, because I'm only used to speaking English when I'm presenting, but I can take questions in Arabic by the end of the talk. So this is my first time in Egypt. I'm quite happy about it. So far, it's going well. They let me in, the customs let me in, so I'm happy about it. So today I'm going to be talking about bug hunting. So it's a topic that hasn't been covered quite well in the Middle East, specifically when it comes to binary applications, hunting for vulnerabilities in binary applications. So throughout my experience in speaking at conferences, usually we have quite a lack in vulnerability research in the Middle East specifically. Everything is kind of oriented in web applications. So I'm trying to kind of give some insight on how to start vulnerability research, and probably you guys can start send us bugs. First, the agenda that I'm going to be covering is I'm going to be talking about the company that I work for, ZDI, which is part of Trend Micro. And then I'll talk about research, and then some tools and techniques that you guys can use specifically to find vulnerabilities in applications and stuff like that. All right, so my name is Abdul-Aziz Hariri. Basically, I'm Lebanese, but I live in Canada, and I work from Montreal, Canada, from my home. I work for ZDI. I'm a security researcher. Been there for the past 5 years. Basically, I do a lot of vulnerability research. Specifically, I'm tasked with binary applications. I don't do any web applications, so I have no idea about web applications in general. So I do a lot of research. One of the most important research that I've done in my past 5 years is winning the Microsoft bounty, specifically for mitigation bypasses back in 2014, 2015. I was tasked with breaking certain mitigations in Internet Explorer, specifically Isolated Heap. And we won the highest bounty, which was $125,000 back then. We had to donate everything to charity, and specifically my portion was donated to University of Concordia in Canada. I graduated from Lebanon, basically University of Valmont, back in 2007. Then I moved to Canada later in 2010. You guys can find me on Twitter if you guys want to communicate with me or anything. All right, so the ZDI, basically, I work for ZDI, and it's a bounty program. And basically what we do is we accept submissions from researchers. So if anyone found a zero-day vulnerability, they would send us this bug. We would make sure that it's exploitable or not. We'll either pay for it or not. And then if the researcher accepts the offer, then we would write a signature for it. And then we would roll the signature in our IPS. In a nutshell, that's how it works. Let's dig a little bit deeper in how it works. So basically, if someone of you guys is a researcher, he would send the submission. The submission would reach our portal. And then I would dispatch this case to an analyst. The analyst would do proper analysis on it, check if it's exploitable. If it's exploitable, then he would write a recommendation to buy it or not. If he writes a recommendation to buy it, then I would offer him a certain amount of money. Once the researcher accepts the offer, and then the analyst would start writing the report for it. Once that's done, we would send it to the vendor, let's say Google, Microsoft, any vendor. Once it's sent to the vendor, then the DV vaccine filter is created, which is the signature for that specific vulnerability, and it gets rolled in the IPS. The vendor has a specific window, which is 120 days to patch the bug. If the vendor succeeds in patching the bug, everything's fine. We would release the information with the coordination of this vendor. If the vendor does not patch the bug, then we would have, by policy, release the information in public after 120 days. Okay, so it's plain simple. That's if it's not fixed. And that's the whole, basically, the steps taken from when we get the vulnerability until it gets patched or unpatched. So in general, I like to show this slide because it shows all the submissions from the countries that we actually get from. Basically, it's almost all over the world we get submissions. This map includes the highly critical applications and the low-profile applications, SCADA applications, everything together. For highly deployed applications, specifically Google Chrome, Edge, Adobe Reader, anything that's a high profile, that's probably installed on every computer. The highest submissions are from North America. China, we get a lot of submissions from China. Egypt, a little bit. Now it's coming to the map a little bit more. For specifically SCADA submissions and highly critical infrastructure applications, we basically get a lot of them from Russia. Russia specifically is an interesting case because we noticed that usually when financially, when the ruble is not doing well with the US dollars, then we start getting more submissions from them because we usually pay in US dollars, which is quite interesting. All right, so let's talk a little bit about vulnerability research. Who has done vulnerability research in the past from you guys? Has anyone found bugs before? Bugs? Binary? Binary or web? Binary, very good. Okay, so let's start with a simple definition of a vulnerability. So it's the quality or state of being exposed to the possibility of being attacked or harmed, either physically or emotionally. It's a fancy definition, but basically it means a weakness. So when you're exposed to a weakness, then you're vulnerable to something. It's as simple as that. In computer science, a vulnerability is a weakness in a system configuration or an application. If exploited, then someone can do illegal or legal actions or access to your systems. It also requires an intimate knowledge of the target application and system, and we'll get to that later. So the process of finding unknown, so the whole research is basically the process of finding unknown vulnerabilities or holes in an application. To do the research, it basically involves skills like auditing code, reverse engineering, fuzzing, all that kind of mess. Vulnerability research is definitely not penetration testing, so let's not mix things together here. Penetration testing is a different game. Vulnerability research is, for me, it can be a little bit more advanced than penetration testing. In fact, penetration testers would use the findings of vulnerability research most of the time. So let's not mix things together. If you want to break things down into steps and how to start the vulnerability research, basically on an application, here's the steps basically. So you get the application, you learn how it works, you identify the entry points. Basically, you have to identify the user inputs, network data that it gets, does it have image parsers, anything like that. Once you identify all the inputs, then you pick one of these inputs and start reversing or auditing this input. Once you start reversing and understanding these inputs, these image parsers, then you start writing tools, basically tools to facilitate communicating with these kind of services. Once that's done, then you can start with the auditing phase. The auditing phase is basically you can do static analysis, dynamic analysis. You can even write a fuzzer, and then you can start finding bugs. Once you find bugs, you report bugs, get paid for it, do full disclosure, whatever you guys want. Then it repeats, the whole thing repeats itself until you start finding more attack surfaces, more bugs, and all that kind of stuff. Basically, it's not as simple as that. Things can get a lot more complicated than this. For example, back in 2017, we started getting vulnerabilities in VMware. Does anyone know what VMware is? VMware Workstation? Excellent. So basically, it allows you to run virtualized operating systems inside a system. So basically, you have a virtual machine inside your host. A lot of people use this for security reasons. A lot of people use this to test software and stuff like that. So we started getting bugs, vulnerabilities in VMware. And we decided in ZDI to expand the research a little bit to start finding vulnerabilities in VMware. So we started breaking down basically how the guest and the host communicate with each other. It turns out that VMware Workstation exposes a channel between the guest and the host called the backdoor channel. It's actually called the backdoor channel. And the backdoor channel is simple. It's basically simple. VMware hijacks two assembly instructions, the in instruction and the out instruction. The in instruction invokes a specific functionality from the guest to the host. The out instructions basically gets the output that the host replies with. It's simple. The backdoor has a bunch of functionalities. One of the functions is called RPCI. And RPCI is basically allows you to execute more advanced functionalities between the guest and the host. And that's where most of the attack surface has been done in the past. The backdoor channel operates in two modes, the low bandwidth and the high bandwidth. The low bandwidth allows you to transfer, basically, if you call a function, then you can only retrieve 4 bytes at a time between the guest and the host. It's very simple, very old. The high bandwidth allows you to transfer more data. Basically, you can give it a pointer and you can get a whole buffer out of the host. So they kind of started with basic functionalities, and apparently they started developing more and more, making it a little bit more advanced. So we decided basically to start auditing that portion, which is the backdoor RPCI, because RPCI has a huge attack surface, a lot of functionalities. One of the problems that we had, and remember when I went back, the slide before, I mentioned tooling, writing tools. One of the biggest problems in VMware is that there's no public tools available out there to audit VMware or to communicate properly with RPCI. Specifically, let's say everyone writes Python here. Python? Ruby? No. Python, yes. So basically, if in ZDI, we write most of the things in Python. So if you want to audit something, write a fuzzer, then basically you might want to write it in Python. If you want to write it in C++, then it's probably going to be a pain. So one of the issues is that there's no much tools there. And we needed a way to communicate better between the host and the guest, easier ways. And basically to script things really fast, write things in Python. So one thing we figured out is basically to write a small Python script that would allow us to execute RPCI commands between the guest and the host. And basically, if we were able to write this Python script, it would allow us to fuzz faster instead of writing a whole C++ application. So what we did is basically write a C extension in Python. Python allows you to write C extensions. Once you compile the C extension, then it's going to give you a Python module. Once you have that Python module, then you can basically send RPCI between the guest and the host, and that's the easiest way to fuzz or to start sending commands. So basically, I compile my C extension. I have the RPC send Python module, and then I can import it easily from inside Python. Once that's done, then I can execute basically an RPCI command. Disk.shrink is an RPC command that you can send between the guest and the host, and it's not privileged. So basically, this was a test. Once that's done, then we use that script for exploit development, for fuzzing, and all that kind of stuff. It even gets more complicated and more advanced. So basically, we also needed a way to debug the RPC commands being sent from the guest to the host. And one of the things that we figured out is basically sniff these RPC commands. So in Windows, there's a bunch of like Wireshark and all that kind of stuff. But in VMware, what we had to do, we basically had to reverse VMware VMX, which basically runs the virtual machine. And we had to figure out where these RPC functions are being parsed. So what we did is basically we reversed that function. We understood that one of the arguments being passed to that function is the actual RPC request. So I wrote a small PyKD script which basically hooks that function, sets a breakpoint on that function, and dumps that argument. So basically the way it looks like, so this is the guest, this is the host. I would run the script on the host, so the sniffing would happen. I would attach it to the guest, and then it would set the breakpoint. Once an RPC command is being sent from the guest to the host, then it's being dumped cleanly. So in that way, I would have visibility on what's being sent between the guest and the host. So this is basically small portions of what vulnerability research looks like. It's huge. Basically, tooling is a very important aspect of it. Something that you guys have to keep into consideration when you want to find bugs is static and dynamic analysis. So specifically, I'm going to start off with static analysis. Basically, static analysis is the analysis of a program when it's not running. It's simple. So you have a piece of binary, and basically you would try to reverse that binary, basically disassemble that binary. In fact, you have two options. You either have source code, and you either don't have source code. If you have source code, then you basically just read the source. If you don't have the source code, then you have to reverse it. So you have to understand the assembly behind it. And basically, in order to do that, you would need specific tools to accomplish that. Personally, I would go with, if I want to reverse something statically, I would do IDAPRO, which is one of the most famous disassembler frameworks out there. There's also Binary Ninja, but I don't really use that. If you want to do source code analysis, I would recommend using the Understand framework. It's not free, it's commercial, but it's really good. It even has code checks in it. So if you have a huge C++ project, you would throw it there, and it would just run a bunch of checks. It would tell you, oh, you have an uninitialized variable here. It might cause you a problem, and then you would just start auditing from there. So static analysis is something that we use on a daily basis, and one of the use cases that I've personally used static analysis is when I wanted to audit Adobe Reader. So who uses Adobe Reader here? Adobe Reader? Okay. All right. So last year, when I was preparing for Pwn2Own is a hacking competition that we do every year in Vancouver. So basically, it's kind of a web browser hacking competition. So usually before the contest, I would go to Austin, Texas, and start preparing the laptops and setting up for the event and stuff like that. So when I was in Austin, I had an idea of basically I wanted to find a new attack surface in Adobe Reader, something that I've never done before. I've found a lot of bugs in JavaScript inside Adobe Reader, but I haven't found an attack surface. And basically, if you find a new attack surface in something, it's like a gold mine, right? Like you would find a lot of bugs. No one has audited that attack surface. It's awesome. So what I did is basically I went to Adobe Reader, the directory, and I sorted out all the files by date, just to see which was the oldest DLL there. So I found out that there's a DLL called onyx32.dll, and basically the last time it was compiled, it was modified as back in 2015. So probably almost 3 years. So what I did, I started reversing and understanding how what's behind onyx32.dll. And it turns out that Adobe needed a way for fast searching to create indexes for certain PDF files. So if you give it a PDF file, it's going to create an index for that behind the scenes. The reason for that is to make the search inside the PDF faster. So if you have a PDF file that's like 200 pages, and you want to search inside Adobe Reader, it's quite fast. It's quite fast because of this functionality, because it creates indexing for it. So I started understanding, like learning how it works and stuff like that. And it turns out that this DLL is being used in multiple plugins inside Adobe Reader, the search plugin and the catalog plugin. It gets even better. Basically, you can communicate with these plugins in JavaScript. So you can force the parsing of these index files through JavaScript, which is great. It's a whole new attack surface. So I started reversing statically, and I started finding some interesting things. Basically, the index file is a binary file format, and it's a property closed and private file format. So basically, when you have that kind of binary file format, it means there's a lot of bugs. Statically, I was able to find a bunch of bugs. So this is basically IDAPRO, by the way. This is a disassembly. And IDAPRO allows you to convert the assembly to C code. So basically, you have C code here. So basically, there's a bug here somewhere. Can you guys figure out where the bug is? Bug. So if someone finds the bug, I'm going to give him a ZDI coin. Bug? No? Okay. So basically, what happens here is that grab 4 bytes is a function that retrieves 4 bytes from a controlled offset inside the file format. So basically, it retrieves a data buffer size. Data buffer size is controlled, so you can give it whatever you want. Later, data buffer size is used in a malloc here, in an allocation. The problem is actually here. Since it's a D word, it's a 32, it's a D word, so basically it's 4 bytes. So if you give it FF, 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 and you add 1 to it, then it's going to wrap to 0. Once it wraps to 0, then malloc is going to allocate a really small object. Okay? Once that's done, what happens is fascinating. So basically, it uses data buff to copy data. So basically, it uses FF, 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 FF to copy data. And basically, it translates FF, FF, FF to a really huge number. So what happens is it basically copies a huge amount of data to a really small object that we allocated through malloc. And that's basically a heap overflow. And that's one of the bugs that we found using static analysis. The problem with static analysis is that it basically takes a lot of time to figure out where to reverse and where to start from. So enumerating all the entry points initially is going to make your life way easier. Dynamic analysis. So basically, dynamic analysis is the inverse of static analysis. So static analysis, you're analyzing something that's not running. Dynamic analysis, you're analyzing something that's running, basically. So you have a debugger, and you're attaching that debugger to a process that's actually running. You're setting breakpoints. You're seeing how the data is being manipulated in memory and all that kind of stuff. There's a lot of tools out there for dynamic analysis, specifically debuggers like WinDebug, OnlyDebug, GDB. If you guys do malware analysis, then you're probably more familiar with OnlyDebug. Personally, I would always go with WinDebug for multiple reasons. WinDebug, I can do kernel debugging, I can do userland process debugging, normal process debugging. And the nice thing about WinDebug is that it supports symbols. So Microsoft releases something called symbols. So basically, if you're reversing a binary application, then it releases the names of the functions. So basically, you would understand what this function probably means, which is quite helpful. All right. So the last thing that I'm going to be discussing here is basically fuzzing, which is something that's probably the easiest thing to start with to find vulnerabilities. Basically, fuzzing is some type of QA, so it's quality assurance in a nutshell. So if you want to test something, do a quality assurance, it's fuzzing. And basically, the ultimate goal of fuzzing is to automate all these kind of tasks, basically just start throwing things at an application, automate the task, and to find exploitable vulnerabilities. So the problem with fuzzing is basically you can find a lot of bugs, but not a lot of bugs are actually exploitable. So you can get crashes all over the place, but these crashes might be useless, basically. So I broke down the whole, the fuzzing process. It's basically composed of 2 things. You have the generator, and you have a debugger. So generator is something that generates data for you to throw at a certain application. And the debugger is basically something that listens or waits for a crash to happen. Okay? So basically, you throw data as an application, and you have a debugger that basically listens, waits, and if there's a crash, it's going to collect that information and tells you there's a crash. It's simple. So basically, you have a framework, debugger, generator, and you have a target. The debugger usually either attaches to a target or spawns a target. So you either attach to a certain running process or you start a whole process. All right. So the generator. So basically, the whole purpose of a generator is to generate random data. So you have a piece of data, and you want to generate as much variance of that data. So basically, there's 2 types of generators. There's dumb generators, and there's format-aware or smart generators. Okay, so the terminology might change a little bit. So some people would just call them dumb fuzzers, and other people would just call them smart fuzzers. I call them generators, basically dumb generator and smart generator. For a dumb generator is basically simple. So let's say you have a file format, a JPEG image. So this is basically a portion of the index file that I've been talking about before. So let's say I want to write a dumb generator. So basically, I would just give it a piece of data, and then it would just start changing bits and words out of it. So let's say I have a generator which picks a random byte and basically just change it to something else randomly. So it's not format aware. It doesn't take care of the format. It might actually damage your whole file. It doesn't matter as long as it changes something out of it. Some logics in dumb generator are composed of, changing one byte, changing one word, flipping a bit, or it can even delete a chunk of binary data out of the file or out-duplicate a certain data. The simplest algorithm is basically, let's say, pick a random offset, change a byte, do that 10 times, and then send the data. That's basically the dumbest way to do it. If you want to implement all that, like all these logics, you can definitely do that in Python. That's what we do internally. But there's tools out there that facilitates this. For example, there's Redamza. It contains all these logics, byte, flip, all that kind of stuff. You don't have to basically, implement all that by yourself. So you can use Redamza, which is online. Basically, initially it was written for Linux and Unix. But there's a port for it on Windows, so if you want to use that, that works as well. The other type of generators is format aware. And by format aware, so let's say I have a JPEG image. So instead of just like flipping random bytes, it basically understands the file formats. So it breaks down the structures. It picks, let's say, one random member of a structure and then just modify one of these fields. So instead of just modifying something randomly, it's actually aware. So it tries to preserve the file format as much as it can. So this is basically when we're dealing with binary file formats. But it actually gets a little bit more complicated than that, specifically when you're fuzzing languages. So let's say you're fuzzing JavaScript or XML or anything like that. Things change a little bit. So you're not fuzzing data anymore. So you're basically fuzzing relationships. By relationships, I mean, let's say you have an object which has a reference somewhere, and then you call something out of it. With the new bug classes, like use after freeze, type confusions, restriction bypasses, data is not basically what we want to fuzz. We want to fuzz how these objects communicate with each other. For example, use after freeze. Use after freeze, so let's say you have an object A, which is allocated, and then you take a reference, you throw it in memory. Later, object A gets freed, so there's no object A anymore, but there's still a reference for it in memory. And let's say something later, an event, uses that reference to call A.B. A doesn't exist anymore, so that's going to crash. So this is one of the new kind of bug classes that are out there. So how are we going to actually fuzz that? Specifically, if you look at this portion of data. So this is one old IE bug. Basically, this is a use after free. It's simple. So you just take a reference to a text box, and then you call add, but you actually pass the same object as an argument. And basically, this triggers a crash. So how are we going to fuzz this? In fact, you're not even fuzzing data anymore. You're basically fuzzing relationships, and you're fuzzing a language. So in order to do that, you have two options. You either have to implement your code in a way that it actually generates another code. So basically, when I started fuzzing Internet Explorer, basically I started writing Python scripts that generate JavaScripts. And then these JavaScripts were fed into IE and basically trying to crash them. You can do that, but it's going to take a lot of time, And basically, you have to implement every object in IE in Python, which is a pain, I can tell you that much. There's also a simpler way, which is basically Dharma. It's an application that Mozilla released, and basically it allows you to implement all these JavaScript objects easily. Basically, they implemented their own language, which is quite simple. And you can implement all these JavaScript objects through Dharma, and then have Dharma generate code for you, which is way easier than you guys implementing Python by yourself. All right. So how do we actually speed up the fuzzing process? So as I mentioned before, basically, you generate a bunch of data, you feed it to the application, you wait for a crash, and you repeat and repeat and repeat and repeat. And that's really, really slow. So imagine you have Foxit Reader, Adobe Reader, or anything. You're basically opening the application, giving a file, closing the application, opening the application, giving a file, closing, until you get a crash. And it's very slow. So how do you actually make things faster? So one day we started getting crashes that looks like this. Specifically, this is a crash that we got in Foxit Reader. And the crash was in convert to PDF x86. The story behind it is that basically, if you give Foxit Reader a specific image format, then it's going to try to convert that image format to a PDF file. And then during the conversion process, a crash happens. So I started investigating more and more to see what's happening behind the scenes. So it turns out that all the parsing, the conversion is happening inside one DLL, which is convert to PDF 32.dll. Okay? The nice thing about this is that it's only one DLL. Like, I don't have to kind of link multiple DLLs together. So I figured out that basically I can write a small application that traps that DLL. So instead of fuzzing the whole application, spinning Foxit close, I can basically just fuzz that DLL directly, and it's going to make things a lot faster, a lot easier for me. It definitely requires a little bit more reversing to understand how the DLL functions, and basically, in this case, it wasn't that complicated because it had two functions basically exported, and everything was being done inside one function. So I didn't have to call multiple functions to do that. You just call one function, it's going to give you an object, then call another function, and that's it. Another use case that we actually ran into is VMware virtual printing. So in VMware, if you're inside a guest and you want to print a document, basically there's a functionality called virtual printing. So you print something, and then it's going to go to the host, and basically it's going to print it out. That's called virtual printing. So by default, I think on workstation is not actually enabled, but in VMware Fusion on Mac, it's always enabled. And if you want to enable it, it requires admin privileges. Yeah. So basically on workstation, it's not enabled, so you have to enable it manually. But in Mac, it's basically enabled. So how does it work? So basically, once you enable virtual printing, it's gonna open a pipe, COM1, and basically when you print, it's gonna send the print job through the pipe, through the COM, to VMX, and VMX is going to spin vprint proxy. Vprint proxy is gonna send it to a DLL, which is a little bit complicated, but that's how it works. The nice thing about it is that vprint proxy runs in medium integrity. So if you guys were able to exploit that, then you're going to get medium integrity on the host, which is quite cool. So you don't need a sandbox escape or anything like that. So how do we actually fuzz that? So logically, when we started getting the cases were triggered from inside the guest. So nothing was triggered from the host. So you had to send the print job from the guest to the host, and you're going to get a crash on the host. In a nutshell, you have everything running on the guest, you have your mutations generator, and then
you would be debugging everything on the host. If you think about it, if you want to automate the whole thing, then you would have a framework, multiple code. You have code running on the guest, you have multiple code running on the host, and then everything communicates with each other. There's a small problem if you're going to fuzz it the way it is now. It's basically whenever you crash a service, then you have to enable it manually. So you have a big problem. Imagine you're fuzzing. You're sending test cases from the guest, and then you have a crash. Excellent. But then what? You have to re-enable it manually. So the whole fuzzing automation process is broken there. So that doesn't really work. So we started investigating further and further. Remember that it actually spawns vprint proxy. So I had a look at vprint proxy. It turns out that you can actually run vprint proxy as a standalone process. And you can give it a pipe. So in other words, you can basically fuzz vprint proxy directly instead of just going from the guest to the host. So let's modify it a little bit. Basically, you have everything running on the host instead of having two different codes running, one on the guest and one on the host. You don't need the guest anymore in this case. So basically, you have your framework. It starts an agent. You have the mutator or the generator, which basically generates test cases for you. And the agent would spin vprint proxy on the machine itself. You don't need to spin any guest anymore in this case. And then just start sending test cases. Once you get a crash, then the agent is basically going to tell you, well, I have a crash. Let's restart vprint proxy again. It's going to restart it again. It's going to start sending test cases. And this is what we actually did. So this is basically a video. Let me see if I can actually click it from here. Okay. So basically, this is my framework. It's going to spin vprint proxy, so it's going to start giving it images, print images. So it's going to do everything on the same machine. If we follow the old way of doing it, basically you have a guest, you have a host, it's going to start sending things from COM1. It's going to be way slower than this, and we're going to have that problem of re-enabling the service again. So basically, this is a lot faster than basically have two separate codes. All right, so conclusion. So basically, in order to get better at bug hunting, you have to basically get better in static analysis, reversing, and dynamic analysis. In order to speed up the fuzzing process, you have to break down the fuzzing process by components. Don't fuzz the whole application. You're going to be wasting your time. You have to fuzz small components, DLLs. You have to fuzz small executables and stuff like that. And of course, once you find bugs, send them to us, and we'll buy them from you guys. Thank you very much. Questions?